This question is a continuation of a look at isomers. Iso meaning same, parts. So in a stereoisomer, we must have the same number and types of atoms. So in the example I have below, I've got something with 3 carbon atoms in it. So these would all be C3. They both have 2 bromines, and they both have 4 hydrogens. Hence, they meet this first criteria, the same number and types of atoms. They also share the same connectivity. And what I mean by that is if we take a look at the bromines that are present in this, one is attached to carbon number 1, and one is attached to carbon number 2. And that's the same in this structure. Carbon 1 has 1 bromine. Carbon number 2 also has a bromine. So they share the same connectivity. Now, this is different than in structural isomers. Just to review those, here I have a substance that also has the formula C3Br2H4. However, the connectivity is different. On carbon number 1, I have a bromine, and so is the second bromine. This leads to what we call our structural isomers that were covered in an earlier program. So let's return to these 2 molecules. They also have a different spatial arrangement of their atoms. We can notice the bromines tend to be on opposite sides of the plane of the molecule. This different spatial arrangement occurs because we have a cyclic molecule that doesn't allow us to rotate without breaking a bond. We can't convert one into the other without breaking a bond. Now, this inability to interconvert occurs in this case because of a ring structure, but it can also happen when you have multiple bonds. Double bonds also prevent the rotation of converting from one into another. So they also exhibit this stereoisomerism. Now, in this particular molecule, the bromines are located on the same side as the plane of my molecule. This is referred to as a cis orientation. So if I was to name this molecule, I would call it cis 1,2-dibromocyclopropane. In this orientation, when I lie across the plane, is called the trans orientation. Trans represents across. You might think of it as a transatlantic flight going across the Atlantic. And hence, I would replace cis with trans in naming the second molecule. Here is but another way of representing those molecules in a lie diagram. So again, being on the same side as the plane is referred to as the cis orientation, and being on opposite sides of the plane of the molecule is the trans orientation. So let's now take a look at this pentene, the presence of the double bond. As I mentioned earlier, it prevents rotation. This orientation, where I am across the double bond, this would be referred to as trans 1,2-dibromopentene. And this one, where the bromines lie on the same side of the double bond, this would be called cis 1,2-dibromobutene. Now, ring structures and double bonds aren't the only thing that can result in a different spatial orientation. That leads us to our next type of isomer, which are called optical isomers. Optical isomers share all of the same characteristics of our cis and trans isomers. What I mean by that is they have the same number and types of atoms. So here an example of what we call optical isomers. Both of these particular molecules have 4 carbons in them. They have a bromine in them, and they also have 9 hydrogens. So they share that. In terms of connectivity, that's carbon number 1, carbon number 2. The bromine is attached to carbon number 2 in both of these particular molecules. So they share the same connectivity. But they have what we call as a different spatial arrangement. You can't convert one into the other without breaking a bond. This occurs because of the presence of what we call a chiral carbon. A chiral carbon can be identified because it has 4 different groups attached to it. In this particular molecule, I could recognize that there's a methyl group up top right there. I have an ethyl group attached. I have a bromine attached. And I also have back here, you can just barely see it, a hydrogen attached. A chiral carbon has 4 separate groups, and they can also lead to this different spatial arrangement, a stereoisomerism. But it leads to a type that we call optical isomers. Let's take a look at how one might draw these. So I'm going to start, in this case, by focusing on the chiral carbon. And there'll be 4 different groups coming off it in a tetrahedral arrangement. So I'm going to show it here with the wedge structure. So up top here is a methyl, CH3, ethyl coming off to the side here, so C2H5. I've got a bromine coming out of the plane of the page and a hydrogen going back into the plane. To draw its other optical isomer, which are also called enantiomers, I do the same thing. I consider a mirror, and I'll start with the carbon, and in that mirror, reflected, I would see the methyl group here. I would see the ethyl group back here. Coming out of the plane of the page would be my bromine, and going back into the plane of the page would be my hydrogen. So here are my optical isomers, or enantiomers. So the presence of this special chiral carbon leads to this property. Let's see if you can take a look at this structure and identify the chiral carbon in it. This is an amino acid called alanine. Let's complete it by interpreting what atoms are present at each of my vertices. So the vertices are represented by carbons. Carbon requires 4 bonds. So there must be 3 hydrogens attached here. There must be a hydrogen here to give 4 bonds to this carbon. And with my last carbon, it's already got 4 bonds. So again, the chiral carbon has to be 4 different groups. And that would lead to this structure. So this particular carbon would be the chiral carbon. So this would also be capable of generating optical isomers. One of the properties of optical isomers is they exhibit what we call optical activity. These 2 particular molecules would rotate the plane of polarized light in opposite directions. That is the only property that they will differ in. They will have similar melting points, boiling points, densities, but they differ only in their optical activity. The last set introduced the term of what's called a racemic mixture. It is a 50-50 mixture of each of these enantiomers. What would happen to its optical activity? Well, being 50-50, 50% of the molecules might want to rotate the molecule, say, in the counterclockwise direction, 5 or 6 degrees. The other 50% would want to rotate it in the other direction. As a result, a racemic mixture actually has no optical activity. So to finish, stereoisomers share the same numbers and types of atoms. They share similar connectivities, but they have different spatial arrangements. And those different spatial arrangements can happen because of a ring structure, or a double bond in the case of cis and trans isomers, or a chiral carbon in the case of optical isomers.